What is retarded potential? Before discussing the retarded potential, I want to discuss something like, as we know, the four-dimension Poisson equation. We know about this equation and this equation. These are two Poisson equations in four dimension. D'Alembert square V, which is equal to this, and D'Alembert square A, which is equal to this. In static case, the above equations can be reduced. Del square V, which is equal to this, and del square A, which is equal to minus mu naught J. Because here we have the time part, so if we remove the time part, then it will reduce to the space part only. Then solving this and this equation, we can get the potential V of R, which is equal to 1 over 4 pi epsilon naught integral rho of R prime d tau prime divided by R, and A, the vector potential mu naught divided by 4 pi J of R prime d tau prime divided by R. When the electromagnetic field is generated by source at time t prime, here this is a source, and time t prime we have some generation of electromagnetic waves, say 1 pm, and reach at point P at a later time t, say 1:15 pm. Then using this relation S is equal to Vt, and this is the origin, and from here to here the distance is curly r, and this is r prime, and this is r. So using this relation, we can say that S, this is the S, which is r, and the velocity of electromagnetic waves, say this is, what is the time? Then we have 1:15 minus 1 pm. So I can write this as t minus tr. So this is the time where the electromagnetic waves can travel from this source to this point, and this is t minus tr time. Now this r divided by c, which is equal to t minus tr, and this tr can be equal to tr, which is equal to t minus r divided by c. So here this time, this is the retarded time, where the electromagnetic waves is generated at tr, and when it reach to the point P, then this time is known as t. So it means that this time t, this one, this measure the potential at point P at time t, and this is the retarded time. Now the natural generalization for non-static case. The potentials must be equal to VR including time, which is equal to 1 over 4 pi epsilon naught, integral of rho, which is prime, and tr, this is the retarded time, divided by curly r and theta prime. And similarly, the potential must be equal to RT, which is equal to mu naught divided by 4 pi, mu naught divided by 4 pi, integral of J, the current density, and R prime and TR divided by R and theta prime. So here the potential, which depends upon R. So from here you can look the potential V at point P. So this is V of RT at time t, which is equal to this, and this R prime, this is the R prime where the retarded time, the electromagnetic wave is generated here, and d tau prime is the volume, this is the volume of the source. And similarly, vector potential, which is equal to mu naught divided by 4 pi, and the current density also depends upon R prime here and the retarded time where the electromagnetic wave is generated here, and d tau prime is the volume of the source. So these two equations are very important now. Here V and A, these are the scalar and vector potentials, and these are the retarded TR here and TR here. So this is the generalization, and we can write these are the retarded potentials. But this is not enough to write down TR here, TR here, and we can say these are the retarded potential. We must use the Laplacian's equation to satisfy these n-homogeneous equations. So let's say now we must show these retarded potential, these equation 1 and 2, to satisfy the n-homogeneous wave equation. Here we are interested to show that the Laplacian equation, this is satisfied with this. So this Laplacian equation, which is equal to this. To satisfy this equation, we consider equation number first and take the gradient of this. So gradient of this, which is equal to this. So this is the product rule, and del rho 1 over r plus rho del over r d type prime, and this is equation number 3. So we have this equation 3, and we can find out delta rho, the first part, if I consider delta rho, and using the chain rule, because rho depends upon time and r as well. So partial rho divided by partial tr dot partial tr divided by partial r, so it will be cancelled out, so there will be, we can write this as a chain rule, so there are no problem. Partial tr divided by partial r, and we know about the tr, and if we differentiate this with respect to r, then we can get minus 1 over c, because t is equal to 0. Partial t divided by partial r is equal to 0, minus 1 over c, partial r divided. So putting this value here instead of this, then del rho, which is equal to minus 1 over c rho dot del rho, and we also know that del r, which is equal to r, and del 1 over r minus r divided by r square. This is from first chapter. So putting here the value of r, so delta rho will be equal to minus 1 over c rho dot will be equal to this. Putting all these values in equation number 3, and we can have. Now equation 3 implies that delta V, which is equal to this. take the divergence of equation number 4. This is equation number 4 and I want to take the divergence on both sides. So divergence of this, divergence of this and divergence of this. And now using the identity, this identity, and apply for this one and for this one. And we have two terms from this and two terms from this because this is the identity. So these are the two terms and from this and the two terms from this. And here this term, this one, delta rho dot, we can use the chain rule because delta rho dot, we can use the delta rho dot divided by delta tr and delta tr divided by delta r. So this is rho double dot and this we can use delta r. So this is previously we have done this kind of chain rule, and this is equal to delta r is equal to this because this is equal to this, and del dot r divided by r, this is equal to this, and del dot this, which is equal to this, the canonical delta, which position dependent. Putting these values in equation number 5, then we can get the equation x. Putting these values in equation number 5, then we have this relation, del v square, which is equal to 1 over 4 pi epsilon naught minus 1 over c, this one, this is the value of delta rho, comes this. If we putting all the values in equation number 5, then we can get this equation. And after some simplification, minus minus plus c square, r dot r a unit vector, this is 1, and rho double dot divided by r. And here minus this rho dot divided by cr square and rho dot this, then rho r dot r, this is 1, and we can get rho dot divided by cr square, and from here we get this. So this and this can be cancelled out, plus minus, and we have this relation. We also know by definition v, which is equal to this thing. This is by definition we know, and if we differentiate this 2 times with respect to t, then this row will be double dot, and this equation 6 can be written like this. If we apply the integration to this term and this term, then we have 1 over 4 pi 1 over c square, this term and this term. So this term is nothing but this is equal to partial square v divided by partial t square. So putting the value of this thing here, partial square v divided by partial t square, then the equation must have the form as. So we have del square v, which is equal to 1 over c square, partial square v divided by partial t square minus 1 over epsilon r. So this integration is depend upon rho. We can take rho outside, and this, the remaining term, is position dependent, so we can write this whole term as rho divided by epsilon naught. So we have this equation, and then if we consider this in the left hand side, del square v minus 1 over c square partial square v divided by partial t square, which is equal to this, and take v common and this term, and we know about this. This is the de-D'Alembert square with v, which is equal to minus rho divided by epsilon naught. So it means that we have considered this retarded potential, and we proved that the inhomogeneous equation for the scalar potential, and similarly one can do the same process for this vector potential.